Now, to begin with this chapter, see what we need to know is we have lots of, you can say, astronomical bodies, right? Lots of them, lots and lots of them. Now, let's restrict ourselves only to the sun, the earth and the moon. Okay, now we all know that sun is at the center and then the earth revolves around the sun. And earth is here, moon revolves around the earth, correct? We all know this part. But see, what we have is we have natural satellites and artificial satellites. Like for sun, earth is a natural satellite, and for earth, moon is a natural satellite. We know this stuff. And then we have artificial satellites, like what we build and we send it up, right? Now, all these objects, whatever we see, they all revolve around one of the objects. Like moon revolves around the earth, and earth revolves around the sun, and sun revolves around the center of galaxy. So basically everything revolves around one or the other object, right? Now, since all of them are revolving, we have, or you can say that we can define a law based on this revolution. Alright, now this was first done by a German scientist called Johann Kepler. Alright, now based on the movement of planets, he gave three important laws. Alright, so we'll go through each of these laws in detail. Now, the first law, what it tells is, this law is called as law of orbits. Alright, so it says each planet revolves around the sun in an elliptical orbit with sun at one focus of the ellipse, like this one. Alright, now basically you need to know what is an ellipse. Simple way of understanding: take a circle, you hold the circle at two edges and then you just pull it. Alright, so it forms an oval, correct? So that oval shaped figure is what we call as an ellipse. Alright, so every ellipse will have two foci. At one of the focus, what we have is the sun. Alright, so clearly you can see that in the picture, right? Right. So this is what we call as law of orbits. Fine. See, the planets will revolve around the sun, and whatever orbit they are revolving is an elliptical orbit. Alright, so this is law of orbits. Second law is law of areas. It says the velocity of planet revolving around the sun is not uniform but changes such that the line joining the planet to sun sweeps equal areas in equal times. So I'll repeat this again. The velocity of planet revolving around the sun is not uniform but changes such that the line joining the planet to sun sweeps equal areas in equal times. See, as you can see in this animation, look at it. So what is happening here? The planet is revolving around the sun, correct? And if you look at it, the farther the planet is from the sun, it covers smaller area, and closer it is to the sun, it sweeps more area, correct? So what we have here is the planets which are revolving around the sun, if they are farther away, the areas, whatever the area they are covering, that will be smaller, because since it is farther, the area covered by that particular planet or any other satellite, you can say. Okay, so any planet with respect to sun, it's more like a triangle, correct? So since we have a triangle, we need to use the formula half base into height, correct? So the height will be more, the base will be less. Now same thing, if the planet is very close to sun, then your height is less, the base value will be more. So area will be equal, right? Now whatever velocity the planet is going, we call that as aerial velocity. Okay, so aerial velocity. So what we say is aerial velocity is always constant. Okay, so if it is very far, then planet moves slower. If the planet is very close to sun, then it moves faster. Alright, so that it can sweep equal areas. So what we say is, with respect to sun, the farthest point is called as aphelion and the closest point is what we call as perihelion. So at perihelion velocity is very high and at aphelion the velocity is very low. Alright, so this is the law of area. This is a very, very important law. Alright, so next we'll move on to the third law. The square of period of revolution of any planet around the sun is proportional to the cube of mean distance from the sun. Alright, so this is what we call as the law of periods. So what we have is, see, let's say we have T to be the period of the planet revolving around the sun. Let's say R is the distance, the mean distance of the planet from the sun. Now according to this, we have T square proportional to R cube. Okay, or we can say T square is equal to K into R cube, where K is some constant. Right. Let's say we have two planets and those two planets are revolving around the sun. Let's say Earth and Mars. Alright, so each of them have different time periods in revolving around the sun, and both of their mean distance is also different. Correct? Now, if we use this law of periods, we can write T1 square by T2 square is equal to R1 cube by R2 cube. Now, this particular law is very important because usually what we do, we consider one of the known quantities, something like moon. We know the period of moon, that's very easy, and we know the mean distance of moon, that's also we can calculate. Now using this, any other planets, let's say we are using some exosolar system planets. Now using this particular relation, we can figure out what is the time period and the mean distance. Okay, this law is very useful. Alright, so these are the three laws. First one is the law of orbit, the one with the ellipse. Second one is the law of area, where it sweeps equal intervals. The third one is the law of periods, where T square is proportional to R cube. Okay, now these three are the three laws of Kepler for planetary motion. Okay, so once we talked about this planetary motion designed by Kepler, then we move on to how Newton, how Kepler, and how these two people, whenever they did their own gravitational laws, how they are related. Alright, so next video you will continue with the same.